depending on the specific data. Yes?
Should we expect to spend more time on subsequent projects, or would this be an adequate amount of time that we should expect?
I believe that this is probably representative of the amount of work going into the projects. However, the concepts are going to get more complex as we progress the complexity of the concepts in class. Does that make sense?
Yes.
So the very basic example is here we did kind of single agent search, right? In the next one, we're going to do adversarial search. So an opportunity to implement Minimax, expect Max, alpha beta pruning, stuff like this. So adversarial search is just a little bit more complicated than single agent search was. This is the kind of progression. See what I'm saying? But the concepts build on each other, which is why we hit these so hard in the class. That's why I did. All right, so there are TA hours. A quick note about my TA hours. I'm there for an hour. It's kind of short. My office is kind of small. I'm happy to spend my hour with you however you would like. We can talk about grad school or whatever. It doesn't matter. I'm there for an hour. I'm happy to help. If, however, debugging your code is what you're looking for, I would recommend talking to the TAs because they're a little more deep in the weeds on the coding part of this than I am. I mean, I'm happy to do it. I like debugging code because I don't get to do it much anymore because it's not exactly what I do as much anymore, but just keep that in mind. So, but again, I'm happy to do it. So I'll spend my hour with you however you want, assuming I'm kind of balancing multiple people there at the same time, but keep that kind of general idea in mind. Does that sound good? Just, they'll probably be better at it. That's all I'm saying. Okay. Good. Good. Clarifications from last time. Any questions? All right, so let's wrap up what we were talking about last time. It's going to get a little more philosophical today. I kind of mentioned, at the first class we had this philosophy, what is AI? We're going to have a little bit of a more philosophical discussion today too, but it'll be relevant down the road as well. So before we get into that though, let's talk about how we would generalize this concept of kind of minimax search to multiple agents where there's more than two, and maybe they're not necessarily adversarial, but not necessarily cooperative either. Maybe it's not a zero-sum game anymore, this kind of thing. So how would this behave? How do we apply the same concepts, framework, and machinery that we've been talking about for general search to this kind of setting? I just want to touch on this really quick. So let's say that here we have 3 players, and they're not necessarily adversarial or cooperative. They just kind of have their own goals, right? But each player is taking turns, so it's very similar to what we saw last time, in that here the red player gets to decide, here the blue player gets to decide, here the green player gets to decide. And then these terminal nodes are going to have tuples of utilities, right? So this node here has utility 1 for the red, right? 6 for blue, and 6 for green. Does that make sense? Okay. So then you still, in this kind of game, want to be able to reason about how you would actually make good decisions, right? Say that you're writing a red player agent or a green player agent, right, or whatever. So how do we kind of search over this? Well, it's very, very simple, actually. We're just going to have each node kind of maximize its utility and make decisions based on its utility. And so we're going to be passing around these tuples instead of one value. And this kind of behavior itself can give rise to what seems more complicated in things that look like cooperation or things that look like coordination or more adversarial behavior, depending. But it's kind of rising naturally from this more abstract notion of utility. Now this is what's happening in minimax search, in true adversarial search. It's just that we have this kind of complementary utility value, right? You can conceptualize minimax search as 2 agents maximizing their utility, where one's utility is the negative of the other's. Right? You see? And then both are maximized. Right? Does that make sense? So this is just that. Right? This is a more general generalization of that. Right? This is the search. Okay. All right, so let's look at how this would work. All right, so we're making decisions here, we go down here, we go down here. Okay. So green has a choice to make, right? So it sees a 6 here, it sees a 2, right? just gonna decide to pick the 6, right? We're gonna keep around this whole tuple. That's the general principle, right? Similarly, had we done it over here, right? Green picks this 2 over this one, right? Et cetera, et cetera. So if we look at this from kind of blue's perspective, blue really wants this 6, right? But is blue going to get the 6? Well, maybe. In this case, it would, right? But it's kind of coincidental because green's going to choose this one based on its utility, not based on blue's utility, right? If we're looking over here, though, what does blue want? Well, blue wants this 5, right? But does blue... Oh, yeah, let's say that. Blue wants the 7. Okay, but does blue get the 7? No, right? Blue gets this one, right? Because green chooses that, etc. Right? So if you're writing an agent for blue, you can start to reason over what green's going to decide. You know these values, or you can estimate these values reasonably, right? Make decisions from that. Pretty simple idea. Over here, we kind of had this notion of, competition, whereas over here it kind of looked like cooperation. But it was kind of just emergent behavior from a more concrete example of actually just messing with something.
Is there a way to make agents directly cooperate with each other? Like they were to look for nodes that would not only be the best of both worlds if they were actively trying to cooperate?
Sure. So you could, we're kind of engineering these utility functions, right? So you have some more complicated utility function that takes into account multiple agents, right? Where your utility is some value plus maybe the utility of Pruning or whatever. I don't know, right? We're kind of designing these utilities to generate the behavior that we would want out of the agents. In this case, we would be looking at like game design, maybe rather than AI agent design, but the concept's kind of apply. Good question. Yes?
If you have 2 entities in a game, right, like the ghosts that both have the same utility function, which is kill Pac-Man, right? Would we even represent them as multiple agents here, since their valuation function or their utility function is exactly the same?
Maybe, maybe not. You could imagine some adversary that is a ghost master, right? A ghost puppeteer. Whatever that has one utility, it's going to have a much more complex action space, right? There's probably going to be an ordering to the ghost behavior that it has to account for, and then there's some combinatorial set of actions per as a function of the number of ghosts, right? Because ghost 1 can go left, right, up, or down. Ghost 2 can go left, right, up, or down. You have to reason over all the combinations of those, right? But it's an option. It's kind of all of it ends up looking like adversarial search. It's just the model that you choose to apply. And that choice, the choices of how you build the model into the system, into the abstraction, has ramifications on potential behavior, on complexity, on implementation, ease of implementation of these things, right? Does that make sense?
Yeah.
Good. Okay, so this is just kind of one way that we might take a different kind of game and cast it into the same framework so that we can use the same algorithmic machinery that we've been developing. Okay. All right, so let's talk about utilities. So this kind of maybe features into both of your questions here. So let's talk about averaging utilities. Why would we, in general, or in some cases, want to average utilities or take some probabilistic approach to utilities rather than just doing minimax all the time? Yes?
You could have 3 independent agents that maybe want to work cooperatively, and therefore averaging their utilities gives the best, for each of those agents to have around the same good utility. Or it would mean the group is performing better overall.
Maybe? Yeah, that's a good point, potentially, depending on how you implement this kind of stuff. Yes.
There's also the possibility for randomness in the decision making, so we shouldn't assume we're always going to get one value over another.
Right. Yeah, that's a good point. So maybe, when you start talking about the real world, we're creating these agents to do things generally for us, if we're not just talking about game playing. Right? Say I've got a robot, I want it to do some search over some notion of utility to perform something that's useful to me. Well, I better, first of all, be pretty good at engineering the utility function. But second, we're starting to talk about the real world, right? And the real world seems less deterministic, right? Or it exactly is not deterministic depending on how deep into the physics world you get, right? But yes.
And I guess it could also be like multiple utilities that could like be co-related, so like maybe maximizing one affects the other, and so finding an equilibrium between the number of utilities.
Sure, maybe there's some more complex notion of utility that takes into account multiple, some conception of different kinds of utility, right? Sure. This kind of behaves more like the real world. So if you had a Minimax agent, it's a robot, right? And it's just trying to maximize its utility, and it's using Minimax, and it gets negative utility value for getting destroyed. What does it do? Well, it probably doesn't need the house, right? Like if I want this robot to go collect things in the world, right?
Crawl under a rock.
But it might just crawl under a rock because in Minimax, the risk that it's had an asteroid land on it while it was outside at probability almost negligible or truly negligible or whatever was too much, right, for it to overcome when it's making its decisions, right? So this is the kind of thing where, you know, if you want real behavior, you kind of have to start reasoning over probabilistic notions of utility, right? So that's generally something, right? We have this maybe MyPython inspired, probably not allowed to say that, bunny here, right? This is a very angry bunny, so we're scared that we're going to run away. It's going to prevent the kind of behavior that we would actually want out of our agent. Okay, so we had talked about, kind of at the beginning of class, this notion of what is a rational agent. A rational agent is something that maximizes its expected utility, right? And so we're getting a little closer to really kind of grasping and understanding what we mean by this, right? We are designing these agents. We want them to act rationally. That means that it needs to choose an action that maximizes its expected utility, given its understanding of the state of the world or the state of its model of the world, right? Okay. So where are these utilities coming from? From us, right? Yeah. We're designing these agents to do something. We want the behavior of the agents to mean something to us, and so we're designing these utilities to kind of encourage the behavior that we want out of the system, right? How do we know utilities even exist? Maybe they don't. Maybe there's some abstraction of something else. Maybe they are true values. We talked about why averaging might make sense. What if our behavior can't even be described by the notion of utilities? I don't know. These are interesting questions. Well, let's talk a little bit about kind of the ramifications of how we choose utilities more concretely. So let's say that we've got two utility functions here, right? We've got the one over here, and then what we've done is we've squared it to produce this tree on the right. Well, if we're running Minimax, then it's really only kind of the relative ordering of the leaf nodes that matters. So let's look at how Minimax would behave in this case, right? All right, so we want to maximize our outcome up here. We go here, takes the minimum, right? That's 0. We go down here, go down here, takes the minimum, that's 20. That we maximize it to 20, right? And so this goes this way, and then it goes this way. That's the behavior. So if we do the same thing over here, we get down, it takes the minimum, right? 0, passes that back up. Similarly, passes that back up. We get a maximum there, 400. The value's different, but the behavior's the same, right? But what happens if we do expect max? Well, let's look. Okay, so we go down this way, we go down this way. This is now expected max nodes, right? And so what's our expected value here is the average, that's 20, right? We pass 20 back up, we look at the average here, that's 25, right? So we do have this behavior, and then we would roll that. But from the blue agent's perspective, the behavior is the same. That's what we saw earlier, right? But if we go this way, what do we have here? The average here is 800, right? The average here is what, 650, right? The behavior's changed, right? it's not just the relative ordering, but it's actually the magnitudes that have started to mean something, right? And so we have to be careful. We need now, as we're assigning utility values to some notion of utility, for our agents, we're designing this utility function to make the agent do the things we expected or wanted to do. We have to start being careful and maybe start to reason over what these kinds of values need to be. So, utilities are functions from outcomes, right, to some real number that are used to both describe an agent's preference and to guide its behavior, right? So in a game, these utilities might be simple. I want to win, I don't want to lose. An agent that maximizes that is doing exactly what he wanted to do. He wanted to win, right? That's the point of that exercise. In some sense, they're summarizing the agent's goals, right? And there's actually a theorem that says that for that any rational preferences, for a definition of rational I'll describe here in a minute, can be summarized as a utility function. Okay, so the takeaway here is that we kind of, as engineers, computer scientists designing these systems, hardwire in this notion of utility, and then we let the behavior of the agent emerge, and hopefully it's doing what we want it to do. So why wouldn't we just let the agent pick its utilities?
How would it do that?
How would it even do that? That's a great question. Right? So there's probably going to have to be some notion of hand engineering what utility means, but say you have a robot, and in the absence of some other notion of utility, it just wants to have a long battery life. Well, conserving its batteries is probably not going to align with your interests for us.
It's going to devour the world to make as many batteries as
Sure, okay, yeah, maybe we've accidentally Skynetted by not telling this robot not to. Unlikely, but it's possible. Why don't we prescribe behaviors? Does anybody have an idea what the difference is, even?
Is that to say, like, if X do Y?
For instance? Yes.
Is that not artificial intelligence, that's just if statements? Which is what we talked about on the first day of class?
Yeah, if it's sufficiently a sufficiently detailed set of probably switch statements, maybe, but that can be broken down into
Very long.
If it's just the longest switch statement of all time, do we care? Maybe not. But it sounds like a pain to engineer, right? Yes.
It's hard to dictate something that could be dynamic, like if the AI recognizes a situation
Yeah.
and can't act on it because you've said no.
Yeah, these are hard problems. We can't generally anticipate all of the scenarios that we would want it to react successfully to, and so we can't even just describe what the proper set of behaviors would be. If we can do that, maybe that works really well. If you can do it easily, maybe do that instead. But in a lot of cases, you're not going to be able to, right?
Especially when you start like combining multiple like contexts, like having a series of different factors that weigh into a decision and kind of like explode.
Yeah. So if you look at like ad-libbing here, kind of natural language processing, right? You want to take some text input or some spoken word input, and you want to understand what was meant by that utterance or that sentence or whatever. How do you lay down a sequence of rules that provides you with the right understanding?
Write every phrase in the English language.
That sounds impossible to do in the time allotted, but that's kind of the far end of prescribing behaviors, right? So the context matters. The context matters in ways that are hard to describe. The context matters in ways that you can't write down, depending, right? Because there's ambiguity in the language that can only be disambiguated by intuition and an understanding of how the language generally works, statistically speaking, maybe even, right? Things like this. So this is why we study these kind of algorithms and not just prescribe behavior. But the notion of hand coding the utility is kind of different, right? It's describing what things are good and what things aren't good, and then allowing the agent itself to kind of figure out how to maximize that, right? And it's kind of invariant in a lot of cases to the specific instances of the problem or the environment, right? Okay, so for instance, let's look at ice cream, right? I think generally speaking, a lot of us would say that, you know, 2 scoops of ice cream is better than 1 scoop of ice cream is better than no scoop of ice cream, depending on your diet, I guess. A lot of people might say that. So, if we're looking at this from a Minimax perspective, it makes sense. You just always go for 2 ice creams, right? But the world might be a little different, right? So you get 1 ice cream, that's generally kind of simple, but maybe in the case where you're asking for 2, it's harder to control, it's harder to keep track of, you might drop it, right? And so this is just one example of where we might want to look at this from a probabilistic perspective, right?
I'm gonna say John.
So this describes kind of, we're getting at a more formal notion of something called a preference. So this is going to be a little more formal, so we're now kind of describing terms. So let's say, in order to allow an agent to have preferences, that we're going to need some notion of prizes. So these are outcomes. Prizes is just a term to describe an outcome in a setting like this, right? And we have, let's define lotteries, which are distributions, probability distributions over prizes, right? So if we have prizes A and B here, then the lottery would be A with some probability P and B with some probability 1 minus P, right? Okay, so I used this notation 2 slides ago, but let's formalize it. If you prefer A to B, use this. If you're kind of indifferent, this would be the notation. Okay. Yes?
Is there a reason why it's curved and not like the normal greater than less than sign, or is that just
It's just the notation.
the notation?
But it's kind of a more abstract notion than like strict greater than from a mathematical perspective. Right? And this indifference, you've probably seen this notation used for like is proportional to in other parts of math, right? So it's kind of got a different meaning. But this will be just the notation of these. Okay, so this is not lottery like the true sense of lotteries. It's terminology. Right? Okay. So what we really need to start talking about is reasoning over kind of distributions of outcomes, right? Utilities over distributions of outcomes. So with this kind of notation, we can start to more formalize what we mean by rationality. So we're going to define some axioms that are constraints on preferences, and we'll say that an agent that follows these axioms is rational. Okay? So here's one, for instance, transitivity. So this says, I don't know why that's not there, but if you prefer A over B and you prefer B over C, then that implies that you prefer A over C. Okay, and you guys have seen this before, right? In your discrete math class, probably. Okay, good. And so you're aware that that is not the same as this, right? And it's not the same as this, right? Okay. All right. So what happens if you don't have this? Well, it turns out if you don't have this, you can lose all your money to somebody who's taking advantage. So let's talk about this for a second. Let's say that you have an agent that prefers A over B and B over C, but then also prefers C over A, breaking this property, right? Then let's say that agent starts with C. Well, then by their preference, that means that they would give you something in order to swap C for B, right? Some small value. So let's say it's 1 cent, right? But they also prefer A to B. So now they're holding B, and you have A. So you get them to pay you to give you A, and then you take B. Or you give them B. No. What is it? They get A, you get B back, right? But then they started with C, but now because they prefer C to A, then you can swap C and A with them again, getting them to pay you for it, right? Everybody starts out with the same thing, or everybody ends up with the same things that they started out with, except for you have 3 of their cents, right? And you just repeat this for a while. So I have a toddler at home that behaves just like this. So we've got a set of like these plastic dinosaurs that he plays with that are different colors. And he kind of would prefer whatever dinosaur he doesn't have at any given time. So you can take one dinosaur that's green, one dinosaur that's blue. If he has the green one, you can give him the blue one and he'll happily trade you. And you can take a yellow one and he'll happily trade you for that. And you can go back to the green one and the blue one. And I have literally wasted a ton of time doing this with him because of it. But the problem is, the real problem is that he doesn't have any money. So, unfortunately, no, it doesn't work out. But we would argue, say that that is not rational behavior. Right? Does that make sense? Okay, that's a true story. Like I did that 2 days ago. Okay. So here's some other ones. We have, oh good, the notation shows up on this slide. Orderability. This means that if you have 2 prizes, A and B, one of these 3 things must be true. Either you prefer A to B, you prefer B to A, or you're indifferent between A and B. Alright, we have transitivity, which we covered. Continuity says that if you prefer A over B and B over C, then there must be some lottery that you would find indifferent to B, between A and C. So you like A best, you like C the worst, and B's in the middle, then there's some lottery that exists between A and C that you would say, yeah, that's kind of function equivalent to B. I'm okay with that. Okay. Substitutability says that if you're indifferent to A and B, then you're indifferent to a lottery that is identical except for A and B are swapped. Does that make sense? Okay. And then monotonicity says that if you prefer A over B, then if there exists a P that's greater than or equal to Q, these are probabilities, then that implies, in the other way, that you prefer a lottery with P for A more than a lottery with Q for A. Does that make sense? Okay. There we got this last one. This is the most complicated.
So that's to say that it essentially you prefer the lottery that has a higher chance of getting A as the outcome?
Yes, informally speaking. If you prefer A over B. Okay. So then there's a theorem that says that if you satisfy these axioms and then meet our definition of rationality, that implies that your behavior can be described as maximizing your expected utility function. Yes.
Sorry, could you explain the lottery syntax one more time? I'm just a little confused.
Sure. So this is just this is A with probability P and B with probability 1 minus P. Right. It's a distribution over A and B. Okay. All right. So we're almost done here. Then we'll take a break. Basically, if you meet these conditions, we call you rational. And then there's a theorem called the maximum expected utility principle, basically that says that values assigned, that if you're rational, there does exist some utility function, and then values assigned by that preserve preferences, both prizes and lotteries. Okay. So let's keep going. How do we start to talk about utility functions for people? We assume people are rational, and there is some utility function that can adequately describe their behavior. So how do we start to kind of gain insight into what that function looks like? Money, exactly. But in kind of a weird way. So, first of all, why would we even care? Yes?
A lot of the time our AI has to interact with humans, so.
Yeah, maybe you're trying to create an AI agent that behaves the way people do, right? So the utilities should kind of align back there, and then yeah.
I think like this image describes something really nice about human utilities. Like we have absolute preferences and we have like relationship preferences. So like obviously we prefer a more expensive item over a less expensive item. But if we get the less expensive item and don't die, it's better than getting the expensive item and dying, right? And so like this image is perfect for that. It allows us, when we think about utilities in a human way, it allows us to have like absolute preferences for like I want to persist in this world or something like that.
Yeah. Yeah, that's a good point. Human utilities are really complicated, generally more complicated than they're going to be in our AI systems. I promise you next. And then yeah.
I think it's likely that when we make stuff, we want it to embody the values that we have, so it's trying to get that across.
Yeah, that's much more philosophical than I was getting yet, right? But if you create something, you want it to embody your values, so you need to know what those mean, right? Yes.
To a certain extent, we want to be able to predict human behavior, but
Kahneman who studies the specific logical flaws in our brains and how we function. So there might be a conflict there.
Yeah, there might be, but you kind of, at the end of the day, want to be able to anticipate human behavior for a variety of reasons, right? Yes.
When they want to solve, like, we build AI to solve human problems, right? So, they should, I mean,
Yeah, a lot of times we want them to kind of align because they're trying to solve problems that are important to us. Yes.
So it could be useful to predict human behavior so we can, I guess, build models and systems that either benefit everyone or exploit everyone.
Or some combination
Yeah.
of those two things, right? Yeah. So that's a great point, and it's more concrete maybe than we've gotten so far. Say I'm designing an agent that has to interact with you, and I need to be able to expect what you're doing in order to make rational decisions that maximize my notion of utility. So it's just some. If we can kind of identify what people's specific utility function is, maybe we can more accurately predict their outcome, right? And then that allows me to engineer systems that interact with them, right? This comes up a lot in like human-robot interaction research. Okay, we can talk about this all day, and it's very interesting, but we'll move on. So some people have actually looked at more formalizing this. How do you actually get to the utility function that people are using? And so let's say we normalize the notion of utility, so rather than any real number, we say that the very, 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 very best possible outcome is a 1, and the very, 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 very worst possible outcome is a 0. I'm going to start to use some math. There's this notion that people come up with called a micromort, which is an awesome name, but basically it's a 1/1,000,000th chance of death. And so then you can ask the question, how much are you willing to pay to avoid a 1/1,000,000th chance of death as a person? So people start to use this concept. We'll go into it in a little more detail in a second. There's this notion that people use called quality-adjusted life years when they're making medical decisions that involve risk. Actuaries use stuff like this all the time. If you're familiar with what an actuary does, this kind of thing. So this is a side note, but for utility function, the behavior is invariant under positive linear transformations. So that may become important later. If it does, I will remind you. So with deterministic prizes, so we're not talking about probabilities at all, we can only order things, right? But that's not really how the world works. So let's talk about this notion of micromort. So one way that people can start to get at this, as I mentioned, is to say, you've got a 1/1,000,000th chance of death. What are you willing to pay to not play the game? Well, you can imagine if it's instead a different percentage possibility, or instead there's something here that's not no change but some positive value, you can start to get insight into what people really value too, right? Anyway, this is kind of how people start to study this. The people, that's 1 micromort. I assume that means that there is a mort, although I'm not positive, but it sounds like a thing we would want to avoid. Yes?
It's more maybe mortality.
So mort, I'm sure, has the same linguistic etymology roots as mortality and moribund and mortician and all these things. Something like that. Right? Is it French? Okay, cool. Which makes it Latin, probably? Okay. So here's an interesting thing about money. We've been talking about money a little bit. Money does not behave exactly as a utility function. But you can talk about the utility of having money. And so one way to kind of get insight into this is that if you have, let's say, this is the utility, and this is notion of money. This is the amount of money you have, and this is $1 million, right? That's going to have some positive utility to you. That's who wants $1 million, right? Wow, very few of you. Wouldn't have expected that. Well, that was your last chance, so what a bummer. No, let's see. But let's say there's some value, right, for $1 billion. And it's probably much bigger, right? you would say?
No, no money, no problem.
Maybe no money, no problems. Depends on who you're listening to. Okay? A lot of people would say that there's some additional utility to having $1 billion, right? But what's the utility of having $1 billion plus $1 million? It's probably pretty close to the utility you would say of having.
But it's not like a linear addition.
That's the issue, right? That this delta here is different than this delta here, right? And so, generally, the worse off, the less money you have, but have a positive value, then the more utility can be ascribed to the smaller quantitative amount. I read this yesterday, and this really struck me. What's the difference between $1 billion and $1 million?
About $1 billion.
About $1 billion. Exactly, right? From a relative perspective, they're very similar, right? So, okay. Anyway, the curve ends up looking something like this, and it behaves differently if you're in debt. Basically, if you're deep in debt, what's more debt to you? So you would be willing to take risks, whereas generally people are pretty risk averse when they have fun. So, anyway, something to keep in mind. This is kind of how insurance works. So if we consider this lottery up here, where you flip a coin, half the time you get $1,000, half the time you get $0, right? The expected value of this is $500. What if I said, instead of flipping this coin, I'll give you $700? What do you choose? Just once.
I take the coin.
You're taking the coin instead of $700?
Feel lucky, so.
You're feeling lucky. Okay, you're rational. So, okay, well, the expected value, so $700 seems like an easy choice, but what if it's $400? You would take $400 over flipping the coin, which has an expected value of $500.
Yeah, you have to pay off bills.
I feel you.
Heat money with that.
Yeah, I understand. It turns out $400 is about what people would pay, or what people would get instead of taking this lottery. That's what people would choose on average. If it's less, they are not going to choose that as often. If it's more, they're going to choose it more often. Probably choose this, but $400 is about where people kind of come out, right? So that difference is how insurance companies make their money, right? Basically, they will buy that coin flip off of you for $400, and because they're flipping a bunch of coins all the time, it means more, something like $500 to them. You both win. That's how insurance works. That's a gross oversimplification of how insurance works, but it is kind of along the right, right? Okay. But you can kind of run into problems with this. So let's say that you have this choice between lottery A and lottery B, where in lottery A, 0.8 of the time you're going to get $4,000, 0.2 of the time you're going to get $0, but for lottery B, you're guaranteed $3,000. What do you choose? Lottery B. Okay, let's look at this one. C, 0.2 for 4K or 0.8 for nothing, or D, 0.25 for 3K and 0.75 for nothing. C. Most people choose C. Okay, so most people choose B and C, but here's the problem. If you assume that the utility of $0 is 0, then preferring B over A, which is what you said, implies that the utility of $3,000 is more than 0.8 times the utility of $4,000. But preferring C over D implies that 0.8 of $4,000 is greater than the utility of $3,000. And those are exactly contradictory. Does everybody see how this happens, right? You just multiply this one by 4. You see? So how can both of those be true? And you still be rational?
Is that quite right though? Because your probability of getting $3,000 is different in B and B.
Well, we're just looking at the orderings here. I have to think about what you said a little more. But both of these are true at the same time in the independent setting. Right? And so since you're assumed to be rational, you have to have some utility function that operates on both, that's consistent in both settings. Right? But it can't be, according to the
fairly,
I mean, I think what you're saying is that it's a little more complicated than the up here. The true cost of this is not just getting $0, but also you might feel pretty dumb about it, right? Because you lost the opportunity. In retrospect, I could have had this guaranteed money. And so the utility function doesn't just operate over the amount of money that you have, but also how dumb you feel afterward. Anyway, okay, so that's kind of where I'll stop on utilities. As I said, it's a little more philosophical, but these are the kinds of things that you might want to start to think about when you're designing complex agents that operate in the real world that may interact with human agents as well. So let's answer a question.
Just a small question. So we're talking human rationality here, but like say we were doing this with an aggregate analysis, they might do the probability between 0.8 and 4K and 0.2 and 0, and realize that that's worth like 3,200 on average, whereas the 100% chance of 3,000 is worth 3,000 on average. So if we do the math here, we would come to the decision that like A is the better, right? On the first example.
Yeah, so if you just do the expected value. Yeah.
Yeah.
But it turns out that people don't choose A
Yeah.
most of the time, because they're not just looking at the expected value.
They're looking at like guarantees more than they don't. Yeah, people are risk averse.
Yeah.
They're risk takers.
Yeah, so are people irrational, or is there more complicated utility going on under the hood? I'm not going to answer that question. I don't know. So I'll have to talk to the philosophers and the psychologists, probably. Somebody that's not me. So anyway, let's take 5 minutes, and then we're going to do some examples of some adversarial search that are going to be very relevant to your potential homework futures. So I would recommend coming back, but let's take 5 minutes.
Yeah, I'm kind of, I'm sticking with 0 on that one, but, you know, I'm not because I have my reasoning in there. Literally, the number of nodes I'm expecting is 32, and they're expecting 28. I was so close, I was like, you know what? It's all just compromising, and it's worse than heuristic afterward. It gives me a 3 out of 3 on that one. It's just on the every other I think that my search is right now. What's really funny is that in their logic they said that medium it expanded just for the 1,000 nodes. Mine did it as 3,000. So I'm just kind of like looking at this when it comes yeah. I think I'm doing something akin to pruning. And then not search from there. I have the C state. I had a bunch of whether you're one of those like rat mazes. Use this for research. It's 21 out of 25 just for the thing. The other points that I didn't hit like were the heuristic one. And you know, that's still like $8. 84. If I have time, I have other work I gotta get done too, so if I have time, I'll go back and I'll fix it. Submit it for now. Yeah, I just didn't look at it. I definitely does like that.
So, I doubt generally you would want to access your because you might end up with multiple paths on the frontier. It may be
I was more
maybe but if you're kind of casting things in general, I don't think I'm not positive at all. Positive that the quality work really well. Yeah, so okay. Alright, let's get started. So we're going to do a Minimax example here, and then we're going to do alpha beta pruning, which I think is the more complicated and interesting part. And it's worth working at least one, if not more, of those in a non-trivial tree in order to kind of get intuition and understanding where that's supposed to go. Okay, so let's just do a real quick Minimax, make sure we're all on the same page. So again, these are maximizers, these are minimizers of the things below them, right? And so we need to go this way. We don't have any information yet, right? And then here, what is it going to choose? 3, right? Passes that back up. So now we know this is at least 3, right? We go down here, no information. We go down here, we pass the 2 back up. This is less than or equal to 2. We go down here, 13. We come back, we say 2. Right? We send this back up. It picks 3. Right? Everybody on the same page? You always slow down. Cool. Then we go here. We know this is less than or equal to 3 now. Right? Down, down, down. This only has 1 child, so it's 15. Right? That should be obvious, but if you're looping over your children, it's just a child. Right? Okay. Sends that back up. So we know this is at least 15. Right? We come back. We go down. Back less than or equal to 29. 2's better. Right? Send that back up. We like 15. Pass 15 up. Right? But we pick the 3. Send that back. Right? So this is at least 3. Everybody with me so far? Cool. I'm gonna slow down anyway because I feel like we're going a little fast, but we'll get through this, then we'll go to alpha beta pruning, which I think is the more interesting part. So, okay. So now we know this is at least 3, but we're not gonna use that information yet because we're not doing pruning. So we'll go this way, we'll go this way. Not yet. We'll prune in a minute. Okay, so this is choosing the minimum among its children, right? Which is 2. Pass this back up. This is at least 2 now, but we don't know what's further, so we need to check. The minimum of 3 is 3. The maximum between 3 and 2 is this node chooses 1. This node chooses. This one chooses. And we finish our search with the value of. Right. And I think our route then becomes down here. Right? Okay, so let's look at the same tree, but we're going to do alpha beta pruning. So let's remind ourselves how alpha beta pruning works. We had kind of started to do some kind of half measures of alpha beta pruning earlier when we were talking about this one's less than or equal to 3, and if I know, because I can see far enough down, my intuition's telling me that I don't need to consider this, and we can start pruning nodes, right? Alpha beta pruning is the formalization of exactly what you're allowed to prune given the information you already have, right? And so it's looking at relationships that are farther apart in your tree than kind of what we were looking at really locally in just one set of children, right? Does that make sense? Because there is more information there. You are allowed to start pruning things that are being influenced by things further away. And alpha beta pruning formalizes that. It gives us an algorithmic way to look at that, right? Okay, so we'll build that intuition here too in a second, but let's just remind ourselves how alpha beta pruning works. So we're picking the min value at some node n, we're looking over n's children, and so our estimate of the minimum of the children is always going down, right? Okay, so who cares about n's value? That would be the max above us, right? At least. Okay. And so then let alpha be the best value that max can get at any choice point along the current path from the root. And that is key, right? Because we're looking at this entire path back to the root. And those are the values that we're asking ourselves to care about. So that'll become clear in a second. But basically, if n gets worse than alpha, max will never choose it at any of the maxes along the path to the root. And so we can get rid of it. Well, we can stop considering the other children. Okay, and we can do the same on the other side with beta for max, right? Okay, so this, at least the first time I thought about it, wasn't super clear. So what I had to do in my AI class a long time ago was work through a bunch of examples to start to build intuition for how this works. I would recommend you do the same thing, but let's start that together with this example. Okay? All right. So I really think it's valuable to look at the pseudocode that we've provided as we do this and really make sure that we're adhering to it. That'll help us kind of go through the process. Does that sound good? Okay. So here we're at a max node, and so that means that we're kind of looking at this code here, right? And so we have some v, it's going to be negative infinity. This v value is just going to allow us to choose the max or the minimum of our children, right? So we won't need to keep track of it explicitly in this example, but that's kind of what it's working for, right? Okay, so basically what we're going to do is loop through our successors. Well, this isn't the whole story because we need some initial value of alpha and some initial value of beta, right? And so let's set alpha here to negative infinity. Let me get rid of presenter v so that I have more space. Is this soon? Okay, that's too bad. Okay, so alpha is negative infinity, is positive infinity, alpha is negative infinity. Okay, that's what we're gonna start with. Okay, so now we need to go over our children, right? We're gonna look at the max of our children. And so we're gonna pass along our alpha and beta values to them, right? And then we're gonna recurse. So we're gonna look at the value of this node here, right? And we're gonna give it our values for alpha and beta, right? And now we're looking in this function. Make sense? Okay, we'll start to move faster as we go, but it's good to kind of be explicit at the start. Okay, so what are we doing here? Well, here we're going to look at the minimum over its children, right? We don't know anything about those yet, so we're going to try to get the first value of the first successor, right? So we go down here, continue recursing, passing along our values, right? This continues. Infinity, until now we finally have something to return, right? So 3 gets passed back up. Okay, so we're now in a min state here, right? So what's happened? Well, we just got back this value b, right? So this value is 3. That's less than our initialization of b, which is positive infinity, right? So now we start to look at our pruning. Is 3 less than our alpha value? Our alpha value is negative infinity, so it is not, right? So we move on. So now we assign beta to the minimum of our current beta and this b. And so that means we're going to change beta, right? You with me? Okay, cool. All right, so we've gone through one iteration of this loop, so now we need to look at the other successor, right? It's, go down, it's 17 gets passed back up. B is the minimum between our current B, which is 3, right? So let's just keep track of the minimum at any given time. And 17, that's just 3, right? It's not less than or equal to alpha, so we're just going to go back. We need to check whether we need to update beta. We do not, right? And then we return B. Okay, so we assign this to 3, we send it back up, right? Okay, now we're looking in here, right? And what just happened is we just got back the value of our first successor, right? Okay, so we take the max between b and that value, that's going to be this value, right? It's the first one we've seen. So is it greater than beta? It is not. Beta is positive infinity. So now we're going to update alpha if we need to, right? And we do, right? So alpha gets updated, right? Everybody with me so far? Cool. Nothing interesting has happened yet, but interesting things will start to happen, and it's good to be methodical here. Okay, so what just happened? We finished this loop once, we have a whole other section, right? So we go down, we have another successor. Similarly here, we're now in here, we need to look at the first child that sent back up as a 2, right? And so B is now 2. An important thing happened that I skipped. We sent this one our current alphas from up here and betas, right? Everybody see that? Okay, so now we're getting this 2 back. Is 2 less than alpha? It is. So we have our first instance of pruning, right? So we cut it off here. We never look down there. Take this value and return it. Okay, so we're getting a 2 back for this max, right? It has its own alpha and betas. Is 2 greater than or equal to our beta value? It's not, but now we've seen all the children, so we can just return the max, right? Which is 3. We send that back up. Now we're in this min node, right? Having returned its first successor, right? Is it less than alpha? It is not, but do we reset beta? We do, right? Because it was the minimum between infinity and 3. That's 3 last time I checked. Okay, but we need to keep looping, right? So go down here. This one gets alpha value of negative infinity. beta value of 3, right? We don't know what to do yet. So we recurse again, negative infinity, right? Get our value of t. I'm squaring the ones that we actually looked at. 15 comes back up. Okay, now we're in the mid node with a value being returned at 15. Is it less than alpha?
No.
It's not. We reset our beta, do we? No. But it's the only value we've got, so we're going to send it back, right? Okay, this is important. We're sending back the value and not the beta value. I don't think it would matter here, but it can cause bad behavior where you're not printing correctly. So send back the value. Okay, so what happened? We're in this max node. We just got our successor back, right? It is 15. Is it greater than or equal to our beta? It is. So what does that mean? We prune here, right? And send 15 back. Okay, so this is kind of our first example. Well, no, let's keep going. There will be a better example here in a minute. Okay, so we send 15 back, right? We're in min here. We're getting a 15 back here. Is it? We're getting a 15 back. Is it less than our alpha? It's not. We can reset our beta if we need to. We don't. But we've seen all of our children, right? And so we pass our 3 back. Now we're at the top. We just received the value of our first successor. Is it greater than beta? It's not, but it does allow us to reset our alpha value, right? Everybody see that? All right. So now we keep going. This gets beta infinity, alpha 3. This gets beta infinity, alpha 3. Okay, so now we're getting this 2 back, right, in our min value. It's our first min, right, so it's going to be b. Is it less than our alpha value? It is. So we can just return b, which is 2, right? So we can prune here. This is a good example of pruning based on a value that exists way far away in the tree, right? This 3 that has propagated through this alpha came from over here, right? That seems pretty far in order to influence our decisions on a completely very distinct branch of this search, right? And so the intuition here is that when do you as a value in a leaf node matter? So if you look at the min operator and the max operator, what those are doing is they're just throwing away a bunch of things, and they're only keeping one, right? So if you're really deep in the tree, the odds that you as a leaf node are going to matter to the search way up high are pretty low, right? Because you have to survive that first min. You have to be the minimum value in that first min operator, right? And then you have to be the maximum value in the subsequent max operator right above that, right? And then you have to, again, be the minimum value in the next one, and the maximum in the next one, on and on and on and on and on, right? And that has to go all the way back to the root of the tree in order for you to influence the decision at the end of the day. So while we saw this 3 way over here, we know about it up here on the path to the root from this node here, right? And so we know the best that's going to happen for this 2, well, for the 6 really, right, is what we're pruning. But it would get all the way back to here, the 2. It would get all the way back to here, right, and then be discarded. You see? This is why we know This is why it matters to pass these alpha and beta values down all the way as you find your successors, and why things that are far away can influence your pruning decisions way out. And so it is difficult for me as a person looking at this tree problem, which is laughably small from a computational perspective, and say, this 2 is really dominated by this 3 over here, in an informal sense, right? But alpha beta pruning is what allows us to make those relationships as we go, right? Okay, so that's starting to build some of the intuition. At least that's kind of how thinking about it helped me a long time ago. Maybe it'll help you just work some problems that's more likely to help. But we have a minute, so we're gonna go really fast, right? All right, so we've got this 2, we pass it back up, right? We're looking at a max node. Is it greater than our beta? It's not, right? So we go down, this gets infinity in 3, we know what it is, we send it back up. This is gonna take 3, right? Send that back up. Is our 3 value less than or equal to our alpha value here? It is equal, which counts, right? And so we cut it off here, return it back, we get a value of 3, and we know that the direction we're going to take is this way. Do you remember when I said it was important to break your ties in a smart way because you weren't getting true values out of this? Right? I just estimated a value of 3 here, didn't I? Well, we did Minimax on this exact same tree, and this value was a 1 in reality, right? So we're really saying it's less than or equal to 3. We know this one is 3, so if we had chosen poorly based on this estimation to go right, which looks like 3, the left looks like 3, it's kind of a tie-breaking scenario, that's actually a 1, right? That's a bad decision. So that's an example of where that matters. Okay, let's stop there. We're out of time anyway, so my next 6 examples won't be worth it, I guess.